we will be wrapping up, fingers crossed, chapter 19 today. So last class we talked about entropy, enthalpy. I think we even mentioned Gibbs free energy. And basically all a bunch of relatively simple math. And we're going to be doing more relatively simple math, relatively compared to like calculus and quadratic equations and stuff. So our standard Gibbs free energy of a reaction, that's what this symbol up here is at the top. The standard change in free energy is a criterion for spontaneity at standard conditions. Who remembers, is it a positive or a negative change in free energy that makes something spontaneous?
Negative.
Negative. We're looking for a negative number for negative is spontaneous. It'll happen by itself. Whereas for entropy, it's positive. We've got three methods. We're going to be covering all three of them for calculating our standard change in free energy. We can use this delta G0 Rxn minus the H minus T and the change in S entropy. We saw something with this form earlier, right? Delta G equals delta H minus T delta S. This time we've added subscripts to say it's for a reaction, and we've added the little 0 to mean that it's standard. So we're operating under standard conditions. We can also calculate directly from our free energy of formation, standard free energy of formation values. And we can also calculate from free energy changes for steps in a stepwise reaction, since G is a state function. So it doesn't matter how many steps you take to get there, all that matters is where you started and where you ended. So that's why we can do it with a stepwise reaction. Even if we went over or if we went under at any point, it doesn't matter. All that matters is where we started, where we ended. So these are three methods that we can use. So we can calculate our standard change in entropy of the reaction and our standard change in enthalpy of the reaction from tabulated values from a table or given. And they're both going to have the same form. So we're going to add up the coefficient times the standard enthalpy or entropy of our products and subtract from that our coefficients times the standard entropy or enthalpy of the reactants. So sum the coefficient times standard entropy or enthalpy and its products minus reactants. So it's just a standard change function. And then we can plug those values in and calculate our standard change of free energy. It's only valid at either 25 degrees Celsius or whatever the standard conditions specify. Usually that's 25 Celsius. But it'll still give us an estimate at other temperatures. For example, we can calculate the change in the standard change in free energy for this reaction and determine whether the reaction is spontaneous at this temperature. What products do we have? Yeah, we have NO2. NO2 is our only product. It does not have a coefficient, so it's a coefficient of 1. So for our delta H and our delta S, our values for NO2 are 33.2 kilojoules per mole, and for delta S, it's 240.1 joules per mole Kelvin. Does anyone see an issue? One's in kilojoules, and the other is not in kilojoules. So let's convert that kilojoules one into joules per mole, just so that we don't have to deal with that later. And then for our reactants, we have NO, and we've got O2. For our NO, we've got values of 91.3 and 210.8. We're going to convert that 91.3. Why did I write a 5? Who knows? We're going to convert that 91.3 kilojoules per mole into 91,300 joules per mole. For O2, our value is 0. And then we have our delta S values. For NO, it's 210.8 joules per mole Kelvin, 205.2 joules per mole Kelvin, and that gets a coefficient of 1/2 in front of it. Didn't turn out as neatly as I'd hoped, but that's okay. So we've got our standard change in enthalpy boxed in purple, and then our other box in purple will be our standard change in entropy. Calculator time. So for our delta H, it's 58,100, and it's negative joules per mole. And for our change in standard change in entropy, it's also negative at 73.3 joules per mole Kelvin. What can we do with those numbers? There's an equation that's partially covered up in the top right corner there. Standard change in free energy of the reaction. It's the standard change in enthalpy of the reaction minus temperature times the standard change in entropy of the reaction. And if you don't remember which one goes with the temperature, it's the one that's got the K in the units, right? That'll cancel out when we multiply it. Other thing we're going to do is change our 25 Celsius into Kelvin. And now we're ready to rock and roll. So our delta G is equal to negative 58,100 joules per mole minus temperature 298.15 Kelvin times negative 73.3 joules per mole Kelvin. So those negative signs will cancel each other out. Negative 58,000 plus 298.15 times 73.3. So our standard change in free energy, negative 55,900-ish joules per mole. For 3 significant figures or whatever it would end up being. Is the reaction spontaneous at this temperature? Yes, we have a negative. We have a negative change in free energy. So it is spontaneous. Questions about those steps? All right. For the reaction in the previous problem, calculate the value of delta G at negative 55 degrees Celsius. Is the reaction more spontaneous or less spontaneous at the lower temperature? And we've got the standard change in enthalpy of the reaction and the standard change in entropy of the reaction given for you. And I'll leave that delta G from the previous problem up at the top too. All right, what's our condition for spontaneity? The reaction occurring by itself without outside energy input. What makes something spontaneous? Yeah, delta G being negative. When delta G is negative, reaction is spontaneous. So if it's more negative, we would expect it to be more spontaneous. So more negative is more spontaneous. This doesn't say anything about the rate of the reaction, just whether it occurs without outside energy input. Our previous value was negative 55,900 joules per mole. That was at a temperature of 25 degrees Celsius. We want to see, is it more or less spontaneous at negative 55 degrees Celsius. You don't actually have to do any calculations for this, but we'll do it anyway. So delta G is delta H minus T delta S. I'm leaving off the standard and the reaction just because I don't want to write them out. So we've got, for delta H, negative 58,100 joules. The thing that we've changed here is our temperature. So negative 55 Celsius is about 218 Kelvin. And our standard change in entropy is still negative 73.3 joules per mole Kelvin. We're leaving off the moles for this one, I guess. So the reason that you don't necessarily have to do calculations is that, just like before, the negatives here cancel out. So we've got a negative term and a positive term. If we make the positive term bigger, the reaction's less spontaneous. If we make the positive term smaller, it's more spontaneous. In this case, the positive term is smaller. So delta G is more negative. So it would be more spontaneous. But we can also calculate the actual estimate. Oh, I put in the wrong numbers for the previous problem. Oops. I put in 7.3, I think. Let me wipe that away. So it should have been 36,200. I'm guessing that there were some people that got that and were like, what? I got a different thing. That's why, sorry. So our new delta G at this lower temperature is negative 42,100 joules. So that tracks with the prediction. This is smaller. G is more negative. The reaction is more spontaneous. So that's one way to do standard change in enthalpy, standard change in free energy of a reaction. We can also calculate it from values of free energy of formation. So our F here standing for formation. And it looks, look at this, look at these. What are those? It's like identical to what the previous stuff, right? We're just using a different value. It's still, the end value's there. We're still subtracting them. It's still products minus reactants. All that's changed is it's gluten-free. It's Gibbs free energy of formation, rather, instead of enthalpy or entropy. So that's pretty nice. Our free energy of formation is the change in free energy when 1 mole of a compound in its standard state. So we have to know what standard states are. forms from its constituent elements also in their standard states. Free energy of formation of a pure element in their standard states is 0, similar to other standard things that we've seen before. I think enthalpy, we also define those values as zeros. I think the reaction is arguably more important. But this little point here, by definition, elements have a standard change in free energy of formation of 0. I think that's also very important. Just in case you aren't given it on the exam on Wednesday for some reason. A reaction that occurs within catalytic converters, Mothman stole mine, thank you Mothman, in the exhaust pipe of a car is the simultaneous oxidation of carbon monoxide and reduction of nitrogen monoxide, both of which are harmful pollutants. So there's valuable metal catalysts in your catalytic converter that break down the exhaust from your car and make it better for the environment. People will steal them and resell them for pennies on the dollar, or try to extract the rare metals themselves. We can use standard free energies of formation from our table here to determine the change in standard free energy of the reaction for this reaction at the desired 25 degrees Celsius. Is the reaction spontaneous at standard conditions? So I will give you some time to work on this. We've got our table down here. We've got our reaction up here. We're using the same n times whatever our thing is for the products minus n times whatever the thing is for our reactants. Okay, calculating our standard change in free enthalpy and standard change in free energy of the reaction for this reaction. We've got products. We've got 2 CO2. CO2's value is negative 394.4. We also have N2. N2 has a value of 0. Okay, so that's our products. We're subtracting from that the reactants. Our reactants are carbon monoxide. We've got 2 of them, so 2 times our value for carbon monoxide. Negative 137.2. We've also got 2 nitrogen monoxides. So plus 2 times the value for nitrogen monoxide. Whoop. Did the arrow the wrong way. It's 87.6. Something like that. So coefficient times the delta G for our product, that's not N2, are 2 times the delta G for CO plus 2 times the delta G of NO. So for our products, it's negative 788.8. For our reactants, it's negative 99.2, and these would have units of kilojoules per mole. So negative 788 minus negative 99.2 are our delta G value is negative 689.6 kilojoules per mole. Is it spontaneous? Very, very spontaneous. Good stuff. We can also, this is our thirdest way of doing it, calculate our change in free energy of the reaction. That's the standard change in free energy of the reaction for a stepwise reaction from changes at each of the steps. We've done this with Hess's law. It was a couple chapters ago. But we've done a couple of things with this style of calculation. Free energy is a state function, meaning that only start and end matter. Final minus initial gives us our value. We don't have to calculate it along the way. So we can calculate our delta G 0 Rxn for a stepwise reaction, just like Hess's law. And we've got some rules. If a chemical equation is multiplied by a factor, our delta G is also multiplied by the same factor. If a chemical equation is reversed, if we flip the products and the reactants, then our delta G changes sign. And if it can be expressed as a series of steps, then our delta G for the overall reaction is the sum of the delta G for each of the steps. So we can just add them all up if it's like a set of sequential steps. Like if I climbed up 4 flights of stairs and then 5 flights of stairs, okay, I climbed a total of 9 flights of stairs. That's sort of, we're just adding them up. It's nothing crazy. We've done this before. Put a red box there in case you want to come back and look at them. All right, so our delta G 0 Rxn for the reaction, we're trying to make this reaction, right, this stuff, red underline, and we've got a couple of reactions that look similar. So we need to flip or multiply these reactions to get this top reaction. If something shows up on the products of one step and the reactants of another step, we can add those together and those ones will disappear. So the thing that I'm keying in on, looking at this problem, is the NO side. So we need NO on the product side. So let's hunt around for some NOs in our reactions. In our first reaction, we've got NO on the reactant side. In our second reaction, we've got NO on the product side. There's a start. We've also got N2O on the reactant side. And it looks like we've only got one source of N2O. And that's in our third reaction. So this might be a better place to start since we've only got one source for it. Another thing to look at is this NO2, our third component. Our first reaction has NO2 in it, and that's the only reaction that has NO2 in it. We'll do that one in red's fine. So we're just finding the components that we need, and then we can flip our reactions around to get what we need. So I'm going to start with this 2N2O reaction. We want 1 N2O. So let's do 1/2 of that reaction. So 1/2 of reaction 3, that will be N2O goes to N2 plus 1/2 O2, our delta G gets cut in half. So we've got our N2O component locked down. We've got 1 N2O, that's what we want. we also need 1 NO2. So we're going to have to flip our first reaction and cut it in half. So we're doing a negative here. That means that we're flipping our reaction left and right. And we're cutting it in half to get rid of the 2 in front of the NO2. So negative 1/2 of reaction 1, NO2 goes to NO plus 1/2 O2. How are we tracking so far? So we've got our reactants side, right? We've got our N2O from our reaction 3 that we moved here, and we've got our NO2 from our reaction 1 that we moved here. On the product side, we're going to have an NO, an N2, and an O2. Fortunately for us, reaction 2 has an N2 on the left side, so that would cancel out with the N2 we have here. We've got an O2 on the reactant side. That'll cancel out with the O2 that we've got here. And we've got 2 NO on the product side that will stack up with the NO we've already got, making it 3 NO. So then our third bit here is just reaction 2. N2 plus O2 goes to 2 NO. And we copy paste our delta G. And just filling in this second line here. So the math part that we would do for this is all this stuff over here on the right. And then in purple, cross out our things that cross out. So just showing that we're ending up with the correct reaction in purple there. Realistically, we can think of it as a set of 2 steps, where this third line, we're taking the N2 and the O2 from our first 2 reactions and turning that into more NO. And then for our delta G, 1/2 times negative 207.4 plus negative 1/2 times negative 71.2 plus 175.2 with units of kilojoules. It's a little messy because I waited until the end to do all the calculations. The delta G, the standard delta G of the reaction is 107.1 kilojoules. Questions?
How did the 1/2 O2 and the O2 cancel out?
We've got 2 1/2 O2s. So I just added those up to make it 1 O2. Okay, so what does the free and free energy mean? The free, if you've been wondering why it's Gibbs free energy, it's Gibbs free energy because it's named after Gibbs, and it's free energy because it's available energy. So the change in free energy of a reaction represents the maximum amount of energy available or free to do work, because there's going to be some loss due to enthalpy and heat and that sort of thing. And so the free energy is just how much energy can actually be done as work. Free as in available to do work. So taking into consideration the amount of energy that we'll lose as heat. The change in free energy is a theoretical limit. So this is the same universe that chickens exist as point masses with no friction and they're perfectly spherical. Our chickens do not exist as point masses that are spherical and have zero friction. That's the physics ideal world. We live in the real world, so this theoretical limit is not exactly accurate. We're going to lose more heat than our theoretical limit of this. It's sort of like our yields in chemistry labs. We can calculate our theoretical yield. If everything goes perfectly, we'll get a certain number of grams out. We're never going to get that number of grams out. Something's going to go wrong along the way. This is the same version, but for energy. So this is an energy version of we're going to lose some stuff along the way. So in reality, we will get less work/energy out. And the reason for that is that only reversible reactions can reach those theoretical limits. Reversible reactions occur in tiny, tiny, tiny little steps. They're incredibly slow. And it's drawn out in small increments in a process that matches the amount of energy produced by the reaction. So this would be like if you wanted to lift a puppy off of the floor to put it up onto your bed to snuggle with it. You would grab the puppy, and then in the smallest amounts possible, you'd be lifting the puppy up. So you'd spend the rest of your life lifting up this little tiny puppy to get it up onto your bed so that it would be reversible. Or you could think of it as if you wanted to make little steps, you would carve out lots of little tiny steps and basically make a ramp out of these little tiny steps that would lead up to the top. The reality is we just don't do things reversibly. So this is an image of what a reversible process might look like. So we've got a gas in here that we want to expand. And if we remove some of the sand from the top of this movable cylinder or piston or whatever it is, right? If we move some of those sand a grain at a time, every grain that we remove, this little thing that the sand is sitting on is going to rise up just a tiny little bit. And of course, in this world, there's no friction because it would take a little bit for it to start moving. So we're just pulling a grain of sand off at a time. We're not taking off 5 grains at a time, 1 grain of sand at a time until our gas has expanded to whatever volume we want it to expand to. So that's the sort of tiny little incremental steps that we're talking about with the reversible process. It would also mean that we could add grains of sand back on to that weight, and it would move back down very slowly. So in the real world, our reactions don't proceed infinitely slowly in the tiniest little incremental steps, partly because we just don't have that much time. Right? I don't want to plug my phone into a charger and have it be done charging in 5 years. I would like it to be done charging in 5 minutes. So we're going to accept that there's going to be some loss of energy for convenience sake. So like when we're using a battery, when we're running any electricity through power lines, there's always going to be some energy that's lost just as heat dissipated into the environment. That's just the heat tax of the universe, I think, is what we talked about on the first lecture for this chapter. And so because of that heat loss, there's always more work that is required to be done since we lose some of our energy as heat. If we want to charge a battery, if we want to charge a phone, if we want to do basically anything, we're always losing some energy as heat. If we're in a cyclical process, so like if we're charging and discharging a battery, like using our phone or a watch or whatever we have, we can return the system to its original state, but it's going to involve more energy put in than we got out of it in terms of work. So we lose energy as heat even with cyclical processes. If we have a chemical reaction that has a positive free energy change, meaning it's not spontaneous, we need to put work in. So work must be put in. That's the minimum amount of work that we would need to make the reaction happen. In reality, we're going to have to put in more work. So this is sort of, if you're moving something, if you've got a big piece of furniture that you're trying to slide across the carpet or whatever, you could calculate, okay, on a piece of paper, this is how much energy it should take to move this thing across the carpet. But when you go to actually move it, if you apply just that amount of force, there's going to be friction with the carpet that maybe you didn't take into consideration. There's going to be air friction of trying to push the thing. And so this is the version of that. There's always going to be a little bit of extra that you need to put in to get the process to happen because of that heat loss. The equivalent of friction. If you've taken physics. That's what my brain is thinking of, at least. So it will require more energy to be put in because you're going to lose some of it. So our standard free energy change applies to a narrow set of reactions or a narrow set of conditions. For example, 25 degrees Celsius, 1 atmosphere of pressure, 1 molar concentration, a completely pure substance, right? We've got those standard conditions. In reality, there are some processes that, if they're standard, are not going to be spontaneous but happen in the real world. So this is one example of that. If you have water that's a liquid going to a gas, it takes energy input for that to happen. It has to absorb energy from the liquid state to go into the gas state. Our delta G is positive, so this process is non-spontaneous. However, if you spill water on the ground and you have a wet floor, the water does not stay there forever until you wipe it up. It will eventually, on its own, evaporate. And that's because our standard conditions is that the partial pressure of water, our pH2O, is 1 atmosphere. That's not realistic. That's just the standard state condition. Under ordinary conditions, our partial pressure is much less than the 1 atmosphere of atmospheric pressure. There's other gas around. we've got a small partial pressure. So even though it's predicted to be non-spontaneous, it does happen spontaneously. We don't have to like shoot it with a heat gun to get it to evaporate. We can make an adjustment to our delta G to predict spontaneity under non-standard conditions. So under non-standard conditions, we have this equation. So our real delta G of the reaction is the standard change in free energy of the reaction plus RT times the natural log of the reaction quotient. And R is the energy form, the 8 pi, 8.314. And using this can help us predict spontaneity with non-standard conditions. We saw something that looked like this, I think, last class. For this equilibrium, this is our liquid in equilibrium with its gas form. And we've got our partial pressure of H2O on the x-axis from 0 to 1. We've got our free energy on the y-axis. Under standard conditions, our Q is always going to be 1. And so our change in enthalpy of the reaction is going to be equal to the change in enthalpy of the reaction in the standard state. In reality, that's not the case. At 25 degrees Celsius, about room temperature, our liquid water is in equilibrium with water vapor, and the pressure is relatively low. So it's 0.0313 atmospheres. The reason on this previous slide that these are the same, these two terms are the same, is because we have plus RT ln Q, and the natural log of 1 is 0, so that disappears this purple term. That's how we get to that. We could do a calculation for this. So our standard change in free enthalpy, free energy, 8.59 kilojoules per mole plus R, 8.314 joules per mole Kelvin times T, 298.15 Kelvin times natural log 0.0313. Might be helpful to unify our units here. So change our kilojoules per mole to joules per mole. I'm getting a value of 3.03 joules per mole. So that just might be a rounding error. Probably a rounding error since at equilibrium our delta G is equal to 0, since this would be at equilibrium. The way that we could show that it's a rounding error is 8.59 kilojoules. If we added this other term is going to be negative. We would have our tens place being our last significant figure, and 3 is smaller than that, so that it would just round down to 0. Probably nobody cared, but that's where it comes from. You could convert back to kilojoules. So 8.59, here's the calculation that we were doing. It would have been 8.587 with, yeah, I'm just showing it with like the kilojoules part because it's maybe easier to see the sig figs part come through. It's really small, and then our last significant figure would be this hundredths place for our kilojoules, since our 9 in our 8.59 is in the hundredths place. Anyway, or maybe it's because I put in 0.15 for the temperature. That could have done it. Nope, that wasn't it. Who knows? I don't. Anyway, it's about 0. The reaction isn't going to move in either the evaporating or the condensing direction. For other non-standard conditions, we can calculate Q and substitute that into our equation. For example, on a dry day, the partial pressure of H2O is 5 times 10 to the minus 3 atmospheres, very small. And we can calculate our delta G. So we're going to use this delta G value, the 8.59 kilojoules per mole. .59 kilojoules per mole plus RT lnq let's just assume that it's a dry day, but it's somehow nice outside instead of being a scorching 110 Fahrenheit. So that's roughly what our calculation would look like. And this whole RTL and Q term is this. So our actual delta G of the reaction on this dry day, not a 100% saturated, 100% relative humidity day, is negative 4543.5 ... joules per mole, so negative 4.54 kilojoules per mole. Which means what? What profound truth have we extracted using this math? It's spontaneous. That's good. And so the big, bold truth that we've pulled out of all of this is that water evaporates when it's dry outside. That's what we've shown here. It's spontaneous. It happens by itself. It's not in the standard state condition of Q equals 1, where we have 1 atmosphere of partial pressure. Consider this reaction. Calculate the delta G under these conditions. And we've got some partial pressures. The answer that was on the slide is wrong. I forget what it is, but it was wrong. I checked. Is this reaction more or less spontaneous under these conditions than under standard conditions? So we are comparing change in free energy of the reaction with standard change in free energy of the reaction to see which is more spontaneous. So we're using that delta G Rxn equals the standard state conditions plus RT ln Q. How do we calculate Q? Or what does Q stand for? It's related to the pressures. It's related to equilibrium. So Q is the reaction quotient. So Q is calculated like K. But it's not necessarily at equilibrium. So our K values our equilibrium constants are at equilibrium. Our Q is the same calculation, it's just not necessarily at equilibrium. It's the only difference. So we want to calculate or figure out what our K expression or our Q expression would look like for this reaction. So it's going to be products over reactants. So concentration or pressure in this case, because we've got pressure, of H2O squared, because H2O has a coefficient of 2 in front of it. Sulfur here is a solid. It doesn't matter that it's rhombic. It's a solid, it gets excluded from our Q calculation. And then our reactants are H2S and SO2. So we'll have those concentrations, or pressures really, with their coefficients raised to the power and all that. So there's our Q expression down in the bottom left corner. So 0.0100 squared over 2.00 squared times 1.50. And it's a Q, so we can just ignore our units. So 0.01 squared divided by 2 squared, which is 4, times 1.5. Our value of Q looks to be something like that. 1.6 repeating times 10 to the minus 5. And that's the value that goes into the Q in our equation here. So we've got negative 102,000 joules plus R with joules per mole Kelvin and 298 K and the natural log of 1.6 repeating times 10 to the minus 5. So our delta G of the reaction, let's plug it all in. This should be negative 129,258.445 joules per mole or whatever. So negative 129 kilojoules per mole, or just kilojoules. Is that more or less spontaneous than under standard conditions? It is more. So it's more negative, so it's more spontaneous. So the relationship between free energy and equilibrium, or delta G of the reaction determines the spontaneity of a reaction. That's the standard state one. K determines how far our reaction goes towards products. If we have a large K, we have a more negative delta G for the standard state of the reaction. Our products will be favored. Sorry, big K. Products favored. This shouldn't be new to us. Small k, our reactants are favored. We can derive a relationship between K and the standard change in free energy of a reaction. Or we can just look at a slide later, I think, that has it instead. There it is. We've got these two beautiful reactions, or equations, sorry. One of those, we've seen that second one before. We haven't seen that first one before. I just completely forgot that I had to do a derivation, and I forgot the steps. So that's the good stuff. We can use that here. it's pretty straightforward. There's only one thing really to plug in. So negative 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of 81.9. So our delta G should be about negative 10.9 kilojoules per mole. So there's our calculation for the standard change in free energy of the reaction. And we've got some temperature dependence. Our free energy change depends on equilibrium constants. Free energy change also depends on temperature. And there's some other fun stuff that we can do with that. So we could come up with this straight line form that just involves some fun, some magic. The fun and the magic is these both have delta G for the standard state of the reaction. You would set them equal to each other. And then I think you divide both sides by RT. And you get this beautiful straight line form. So it looks kind of like y equals mx plus b. That's why it's the straight line form. So it looks like a linear function, because it is a linear function. But it's an estimate. So this is not going to work for all temperatures. It's useful over a limited temperature range. Our slope is this front term. Our intercept is this back term in their normal y equals mx plus b spots. And this means that we can find our standard enthalpy of the reaction and our standard change in entropy of a reaction if we measure K as a function of temperature. So the kinetic stuff that we were doing, if we do that at a set of different temperatures, a bunch of different temperatures, and calculate out, figure out the equilibrium constants for those reactions, then we could plot those and get our slope and our y-intercept, and that's how we would get our delta S and our delta H, which, given how well our kinetics stuff went, I'm sure would go very well. We also have a 2-point form. I forget the other equation that we had a 2-point form for, but if you just subtract two of those, and then you condense the natural log stuff, temperature 2, temperature 1, and if you know the standard enthalpy, standard change in enthalpy of the reaction, then you could calculate K2, for example. Or if you had two K values, you could estimate your standard change in enthalpy of the reaction. Questions? That'll do it for chapter 19.